So hello everybody. We're going to be hello everybody for everybody who's watching the live stream right now. I'm going to be doing another one of my series, which is just a little bit of a study session. For today's topic, we're going to be studying a little bit more electricity because I haven't, apparently I haven't got the sufficient amount of knowledge the last time that I studied this. So I'm just going to study some more, just for fun. Just for fun. So I'm going to set a timer for myself. Okay, we're gonna have 15 minutes. Okay, good. So basic electrical quantities. Current, voltage. We talked about. I talked about current and voltage in the last video. Okay. So we're just going to be like. Oh, by the way, credits to Khan Academy for this. Just going to be reading a bunch of stuff. Let me just get the whiteboard. Here we go. Okay, so we know that there's there is what we call charge. Okay, apparently it's the source of for a force, and we fundamentally know that the opposite types of charges, they basically attract each other, while the like charges repel each other. So this is actually also what we discussed with conductors, the copper wire. Just let's do a little bit of a review on what I just read. Okay, what we just read today. what we just read earlier. Okay, so we have charge and conductors. Okay, so what is charge? Okay, charge is basically just the source of force. Okay, so we could just let's say you have force. Okay, the source of that is charge. Okay, the source of that is charge, and we know we get charge from calculating. Okay, we know that charge from we know that charge is involved in calculating currents. Okay, because currents is equal to charge. Okay, q q per second. Okay, which is charge per second. So if we disregard all of that, we also will have what we call conductors. Okay, excuse my illegible writing. Okay, so we have conductors, and conductors is basically this thing. Okay, they're basically this thing that, okay, they are material that has atoms, like copper, for example. Okay, that has atoms. So let's say this is the nuclei, and we have a couple of fields here, and the very outermost electrons that are outside, okay, or what we call valence electrons. These valence electrons can be ripped apart. Okay, they can be ripped apart from the nuclei of the atom. Okay, of, let's say, a copper atom. You can easily rip them apart. And apparently one of the examples of a good conductor, okay, a good conductor is metal. Okay, metal atoms. So let's say you have a metal atom right here. Let's say you have a couple metal atoms. This is the valence electrons. Okay, this is the valence no, that's a negative. Okay, so this is metal atoms, valence electrons. You can easily pull them apart, and they can just sort of like just be free from their nuclei, and that's what you call it, the conductor. Valence electrons that can easily pulled apart from the atom, from the source atom. And now also we have what we call insulators. Okay, so insulators are basically, so you have, let's say you have a water atom. Okay, valence electrons. Okay, the outermost electrons that can be located near the nuclei of the let's say water atom. They can easily be pulled apart. Okay, they can easily be ripped away from the nuclei, because these electrons, when you have electrons in insulators, they basically just stick to their nuclei as much as possible. So when you apply an electric force, okay, when you apply an electric force on these, it basically just, apparently it breaks. Okay, it just breaks. The electrons just break down, as far as I understand it. Or at least that's how I understand it. So let's get back to reading. Okay, so let's go back and try to review what currents mean. Okay, so currents are basically just this the moving of ions. Okay, moving of ions, whether it be positive or negative. So you can see we have a wire right here. Let's use another copper wire as an example. This is a copper wire. Okay. This is a copper wire, and you insert a battery right here. You insert a battery right here, and you imagine a boundary line. Imagine a boundary line, and you're going to count. So let's say you have a lot of electrons right here. Okay, a lot of electrons is negative. Obviously, we have positive and negative. Positive and negative. Positive on the left side, and negative on the right side. So this is going to go to the electron current. The electron current is going to go to the left. But the conventional current, okay, conventional current, or how it's mainly described, or mainly described is currents are positive charges that go this way, that go right. Okay, that's basically it. We can also derive this. So we can also derive currents as this derivative right here. We got I dq dt. Okay. Yes, I believe that is it. So I'm right. This means charge. Okay. The Q means charge, and this is time. So current is basically just current is equal to charge over time. Okay. I equals dq. Okay, over dt. Let's just copy this. I'm going to try to make an understanding of all of it. So we have this mg So we can make an analogy of voltage being just the acceleration due to gravity. Yes. Acceleration due to gravity times the change in height. Okay. So we have gravity acceleration times change in height. That's basically just voltage. So this is actually the same analogy that I made. Okay. That I extracted from Khan Academy. It's the same one. The mountain, such. Ball at the top of the hill rolls down. When it is halfway down, it has given up half of its potential energy. Okay. For mass m, okay, so voltage resembles gravity. For mass m, a change of height corresponds to a change in potential energy. So first, let's try to clearly define what this potential is. Yes, we can basically imagine voltage is this, like this. Hold on. So you can basically imagine voltage like this. Let's say I have a charger, okay? Let's say I have a charger, okay? Sorry for the bad drawing. Okay. Let's say I have a charger. This is the cable, okay? Cable. Just the plug. This is the no, this is the plug. This is charging for the charging port. Okay, so we have a charger right here. We can imagine voltage and starting here. Okay. So this is just an example, of course. Okay. So we could just say that the electrons are coming here. Okay. This is the battery. This is the battery. So okay. So this is the battery. If you imagine the long part of the battery right here, of course, if you plug it in if you plug it in, if you plug the charger in, if you plug the charger in, the charger is basically just going to get electrons, and it's basically just going to get electrons. Okay, this is an electron. It's going to get electrons here because this is the positive side. and the electrons are negative, so it goes in. Okay, so the electrons basically go in, and let's say that okay, they go in smoothly. Okay, that's the that's the ideal voltage. That's the ideal sort of concept of voltage. But voltages, they basically lose their potential energy along the way because they sort of behave like gravity, as they said. So we could imagine voltage as being sort of a bent charger, okay? Well, bent charger cable like this, okay? So let's make an example. Um, so let's say this charger again, okay? Sorry for my bad drawing. Let's say that the charger is bent, okay? Charger is bent like this, okay? This is the this is for the charging port. So the charger is bent like this. Now, this is more accurate representation of voltage, I believe, from my own understanding, because the electron is the electron is basically just going to come into the charger, and along the way, as it sees sort of the bent parts of the charger, the electrons are sort of losing their potential energy. So you can imagine this. So we can imagine like this is what okay. So this is the way the little squiggly lines are supposed to happen, I believe. So this is how I imagine voltages to be, but it's actually the more accurate representation of it, I believe. So yeah, like that. Okay. No, I think it's like here, but you get the idea. This goes there, and this spirals, goes in spiral, and that's only from my own understanding, though. Of course, it's only from my own understanding. So now we're going to express the voltage between 2 points mathematically as the change of energy experienced by a charge. Okay, so apparently voltage is derived mathematically as this change of energy experienced by a charge. I'm going to try to find out what this exactly means. It's an intuitive description of voltage in a nutshell. Change. So this the delta sign basically means change of energy experienced by charge. Power is defined as the weight energy. Okay, so power is basically just a derivative. It's basically power is I believe that it is. Yeah. Change in energy. This basically just means change in energy. Change in energy over time, or transformed or transferred, transformed or transferred over time. So apparently we measure power. We measure power by joules per second or watts per second. I don't know if both of them are the same, but that is what the text says, joules per second. So we can compare this to charge, okay? We can compare this to currents, which is charge per second. Now we're going for joules per second, or watts, slash watts. Yeah. Experienced by charge, it's voltage. Electric. Circuits can transfer power. Okay, so let's first try to define what electrical power is from my own understanding. Okay. Hmm. So electrical power is basically this. It's apparently the equation DU So du, which is basically uh, or was it dq? Yeah. So dq dt. So electrical power is just voltage times current. Right? Am I right? So this is experienced by charge, the change of energy. Yeah, I knew it. This was a Q. It's actually a Q. So we can. So power is this VI equals the change of energy that is experienced by charges times which is voltage. That's the power. That's the electrical power. Okay. So this is voltage. This current. It makes sense that is VI because this is voltage. That's a sign for voltage. This is a sign for current. I is a sign for current. So we have current, which is basically just the of rate of charges over time, and that's going to give us electrical power. Okay, and apparently this is the unit. The unit of electrical power is measured in watts. Okay, that's measured in watts. So it's going to take a short little break from here. I'll be back after a short break. Alright, so we're back again, and we're just going to continue where we left off right here. Okay, so we're done with the electrical power. Let's move on to the next lessons. Okay. So we have this. The small numbers compared to everyday experience. Let me just try to review myself on scientific notations. Hold up.
There are two whole Khan Academy videos on what scientific notation is, why we even worry about it, and also goes through a few examples. And what I want to do in this video is just use the ck12.org Algebra 1 book to do some more scientific notation examples. So let's take some things that are written in scientific notation. Just as a reminder, scientific notation is useful because it allows us to write really large or really small numbers in ways that are easy for our brains to, one, write down, and two, understand. So let's write down some numbers. So let's have 3.102 times 10 to the second. And I want to write it as just a numerical value. It's in scientific notation already. It's written as a product with a power of 10. So how do I write this as just a numeral? Well, there's a slow way and the fast way. The slow way is to say, well, this is the same thing as 3.102 times 100, which means if you multiply 3.102 times 100, it'll be 3102 with two zeros behind it. And then we have 1, 2, 3 numbers behind the decimal point. 1, 2, 3 numbers behind the decimal point. And that would be the right answer. This is equal to 310.2. Now, a faster way to do this is just to say, well, look, right now I have only the 3 in front of the decimal point. When I take something to the times 10 to the second power, I'm essentially shifting the decimal point 2 to the right. So 3.102 times 10 to the second power is the same thing as, if I shift the decimal point 1 and then 2, because this is 10 to the second power, it's the same thing as 310.2. So this might be a faster way of viewing it. Every time you multiply it by 10, you shift the decimal to the right by 1. Let's do another example. Let's say I had 7.
Okay, so alright, so I'm going to have to end this live for now, but do expect a few more parts of this, but this we're going to be concluding this live. Okay, so thank you guys for watching.